What is a signal? Any sign, action or sound that conveys a particular message is in general terms called as a signal. For example, a sound no, an action no, or like this, and a sign like this conveys no. So this is in general sense a signal. In signals and systems we are studying engineering. So in systems, what do we say? That a signal is a source of information. It is a source. For example, let this be speaker. So this is the source that is emitting sound waves. So a source of information is a signal, which is generally a physical quantity which changes with respect to time, temperature, space, or some such independent variable. Okay, so this is in signals and systems. Mathematically, what we do, it is a function of two or more independent variables. Very simple. For example, if we take xt, which is x0 cos omega t, here t is the independent variable. So with time, this value is changing. This will be like this. We know this is very common. This will be like this. Okay, here. Okay, so this is how we understand signal, in systems, and in mathematics. Mathematically, it is expressed like a quantity which varies with respect to some independent variable. That independent variable can be time, that can be space, that can be temperature. It depends on the system. We can have so many examples. For example, sound waves. It is basically compression and expansion. So let's say it is the pressure is denoted by P0 sine omega t. With time, it is changing. You know this, how it is drawn, like this, then again compression. So sound wave can be represented like this. We have studied so many electrical signals like voltage. Voltage can be represented as V0 cos omega t. This is also a signal. So there are so many signals, and with such a big variety of signals, we have so many mathematical expressions for them. Now, there are basically two types of signals. If we come to our signals and systems, there are basically two types of signals. First is called continuous time signal. Continuous time signals. And the second one is called discrete time signals. What are continuous time signals? First, the independent variable. The independent variable is continuous. This is the first characteristic. If we are talking of time, time is continuous. It is not defined at some discrete points. It is continuous, 0 to up to whatever value you go. Second, the signal that we are talking of, and the signal is defined for continuum of values. Defined for continuum of values. That is, in short, you understand that if this is time and this is the signal, let's say x, then t is continuous. It is not defined at discrete points. It is continuous. First. Second, if this is our signal, then it is defined for all values. It is not defined for only few values. It is defined for all values. So this is continuous time signal. And we generally denote it like this, x and in small brackets t. Okay. Now, second is discrete time. Here, in continuous time, the independent variable is continuous. Here, the independent variable is defined for discrete values only. That is, if we are talking of time as independent variable, then it is not defined throughout. It is defined at certain fixed values only. Let's say 1, 2, 3, 4. So at t equal to 1, t equal to 2, t equal to 3, t equal to 4. This independent variable, we are talking of time here, it is defined for discrete values only. Second, similar to this, the signal is defined at discrete values only, discrete values only. Okay. So if the discrete values are at 1, 2, 3, 4, signal is defined at this, signal is defined at this, signal is defined at this, signal is defined at this. Okay. And we denote it like this, x n in capital brackets. Okay. So at n equal to 1, the value is something. At n equal to 2, we have another value. This is discrete time. So this is continuous time, this is discrete time. This is the first basic understanding of signals when we are talking of signals and systems, that the signals are defined as either continuous or discrete, and based on that we have systems. We have continuous systems and we have discrete systems. Now we just understood what are continuous time signals and what are discrete time signals. Now let's suppose we have a signal. Obviously energy will be involved to emit a signal, to generate a signal, to transmit a signal, to receive a signal, to recreate that signal. Everywhere, whether it is a continuous time signal or a discrete time signal, what we'll require is energy. And with energy, because we'll having time as the independent variable, because of energy, what we'll be defining is power also. So what are the energies associated with a continuous time signal and discrete time signal? Let's understand. Energy, let's write it like this. For a continuous time signal, let's say from T1 to T2, this is the signal we are transmitting. This is T1 and this is T2. We want to know what is the total energy in between T1 and T2. Then it is given as T1 to integration T1 to T2 xt mod of xt. Why mod of xt? Because this xt can be complex also. We do have this signal is like voltage. If you remember, voltage signal is V0 cos omega t plus j sin omega t. So generally the signals are complex. So for complex signals we need to have the mod value. So this is mod of xt square dt. This is the energy. If we have voltage, we'll take this particular expression and then integrate it. And power is, time average power is this Et by the time interval, that is T2 minus T1. So this will be 1 by T2 minus T1, T1 to T2 xt square dt. Okay, so this is the expression for energy and this is the expression for power. Okay, you must note this down. Now the same thing for discrete system. Let's see. In continuous time signals we integrate. You have studied integration, you know, for continuous time integration means from here to here, all the area covered under the graph between this point and this point. In case of discrete signals, what we'll do, we'll add all the values. Simple. So energy will be, let's say we write it like this, energy. So energy will be summation of n equal to n1 to n2 and again mod of, this is our signal xn, so square of this. Okay, there we had integration, here we have summation, and power will be same divided by the time interval. But one thing you'll have to understand, let's say this is n1 and this is n2. Now n2 minus n1, then this will be left behind. If you write down n2 minus n1, this won't be this interval because this signal will be cut off. So what we do, we take this one n1 minus 1. So n2 minus n1 minus 1. So that will be the time interval. So it is energy by n2 minus n1 minus 1. Okay, or you can write it directly like this, n2 minus n1 minus 1 summation n equal to n1 to n2 xn square. So this is power for discrete signals. Clear? Now what if we have to take from minus infinity to plus infinity? Here we have taken from T1 to T2. What if we have to take, if this signal is for infinite time? Nothing much here. What we'll do, let's say we write t1 and t2 as t. So t tending to infinity, this is minus t to t, and here we have xt square dt. Simple. We'll have to take this limit, and power will be similar to it. It will be like this: limit t tending to infinity. This will be 1 by this minus this. So this is 1 by 2t, and here we have minus t2. Okay. Now from here only you can see, if this is not infinite, if this is something less than infinity, this is a finite quantity, then this will be 0. That is, if energy is finite, this energy is finite, then average power will be 0. Okay. And in case of discrete signals, similar to that, En, this will be n equal to, let's say, minus n to n, where n tends to infinity. Okay. And power will be, you have seen, this is limit n tending to infinity. That was n2 minus n1 minus 1. So this will be now 2n plus 1. So this is 1 by 2n plus 1, and this is same. Okay. This n2 minus n minus 1. So we have put the value and got this 2n plus 1. Clear? This is the expression for energy and power when we have infinite signal. That is, the signal is very large on time scale. So one thing important that I told you, I discussed that time, that if infinite energy for infinite time, if this energy is finite, our power will be 0. Clear? But if P is not equal to 0, it has some value, then it means this is infinite. From that expression only. So this you should keep in mind.